Dr. Torres received his BS in mathematics and BE in industrial and chemical engineering from the Pontificia Universidad Católica de Chile, and his MS and PhD from the Massachusetts Institute of Technology in food microbiology and food engineering, respectively. Dr. Torres has more than 30 years of process engineering research experience. He has authored 126 peer-review articles, 51 book chapters, and 16 technology dissemination articles. His expertise includes the statistical design of food processing, packaging, and storage, application of non-thermal technologies in food processing, specifically high hydrostatic pressure processing, and the production and utilization of biomolecules and biopolymers. Well, I remind everyone, please to mute your microphones and enjoy the presentation of Dr. Torres.
Good morning. Thank you for joining. Maybe it's good afternoon or good evening where you are located, but I'm calling you from Houston, Texas, where I have just moved recently from Oregon, and hope that you are enjoying good weather like I'm enjoying here in Houston. One of the things we're going to talk today is the use of probabilistic engineering, and the reason for that is that if we don't do that, it would be very challenging to meet consistently your requirement for product quality, safety, and shelf life. And I will illustrate these principles using moisture management as an application. But this concept can be used in any situation you can find. I haven't found one yet that I cannot deal with these principles. And so I have my students learn too. This work is also a collaboration with colleagues at Tecnología Monterrey, Jorge Velti, and my current postdoc there, Veronica, who was introducing this webinar, and Gonzalo Velázquez at Cicata Querétaro. Come on. Okay, so what we're going to talk about is failure probability of whatever decision you make. And when I say risk or failure probability, I'm not talking only about microbial failures, which is always in our mind, but any kind of prediction failure. So let's talk about failure probabilities. I mean, if we take a flight, and I take a lot of flights in my working life, the probability of failure is in 1 in 20 million. If you eat a meal, the risk is much higher. One of 6 people may get food poisoning from a meal, and that's our responsibility. There's something we need to do something about it. We've been improving significantly in the last few years, but we still have much work to do. And when it comes to new product launching, you will find that the consumers you are trying to sell the product, even for all after our work and doing shelf life studies and consumer testing, all kind of work that we do to make sure that our product will be successful in the market, we find that about 70 or 90% of our product will fail. And my point that I want to make today is that one reason that the airplane flights are so much safer is that the airline industry uses a lot of modeling to do their design of the flight systems, and which includes a lot of probabilistic engineering applications to make sure that the airplane will be as safe as possible. We are beginning to do some of that in the case of food, and some of the HACCP concepts are beginning to help, and other related technologies, but most of them tend to be fairly descriptive and not quantitative enough and not probabilistic enough. And obviously, the consumer rejection, the problem is that we're dealing with human beings, and still we are very far away from being able to predict the behavior of human beings. We are fairly unpredictable. So let's talk about this moisture management calculations. And Typically, what we've done is following a deterministic approach in our calculation. So let's say we want to calculate some output data, whatever shelf life, microbial load, the permeability of the packaging material, whatever property that we need to estimate for the process or for the product, we're going to go through a series of calculations. For all these calculations, we're going to have some data, some input data. So it could be the composition of our product, it could be the storage temperature of our product, the processing time, whatever parameter you will have an input. In traditional way we've done is just use the mean values of all those properties, go through the calculation, and then we get as an output a single value. Okay, but we know that all this input data has variability. It could be small variability, like in the case of the blue line here, or it could be much larger in the case of the other color lines there. But what we're doing is just using the central value of these properties and executing all those calculations, ignoring the variability, which I consider to be the most important source of data that we need to use when we design a product or a process or a storage condition. So question could be, well, if I know the variability of my input data, could I go through the calculation and afterwards try to, based on the variability of the input data, estimate the variability of the output data? Okay, so yeah, I mean, let's say that we have one of the calculation steps is just a simple sum. So let's say if I'm summing two values of moisture content, for example, to calculate a certain average. I know that if this is distributed with a normal distribution with these properties for both samples, I could estimate what will be the distribution of the sum using this simple formula. Okay, so the new mean would be just the sum of the mean and etc. for the rest of the properties. So it's predictable for the case of a sum. Okay, and it will be a fairly easy prediction to do, just involving a few sums. In the case of the division function, which we're probably going to have in some of our calculation steps, it gets a little bit more interesting. Okay, so now it's just not so simple, but it's still possible. In the case of the multiplication function, you can see now that it's getting a lot more complicated, and I would say that very few food science students and food science industry personnel would be able to manage the case of a multiplication function. And keep in mind, the calculations are much, much, much more complex than just simple sums, divisions, and multiplications. So, and the calculations steps multiple. So one output from one calculation step will be used in the next calculation step. So things will get ugly very, very, very quickly. So the conclusion of this simple introduction is that the idea of using deterministic calculation procedures based on single value, and as I said, the single value is typically the average or some other central value description of the data. Or in some cases, we do even worse, in my opinion, is when we're trying to do this calculation based on extreme values, because those extreme conditions are rare and they are extreme by the definition of the value, and then we'll end up either over-processing or under-processing or under-designing a product. So it's not a good idea to use extreme values to estimate a process. It's not a good idea to use a mean value because, as I always say to my student, mean value calculations are really meaningless. Okay? So what I'm proposing you to do is a probabilistic approach. So nothing major has changed. So it's the same calculation steps that we've been using always in our deterministic calculations. But now we're going to repeat this calculation many times And each time we do the calculation, we'll sample randomly from the values possible for each of the input data. And those input data can have many different forms: a normal distribution, a uniform distribution, a list of values, which I really like. I mean, a lot of youth that work in industry will find that you have over time an accumulation of data. Let's say you've been measuring the moisture content of a certain ingredient. Well, after 1 year working for that company, you will have thousands of values of those measurements. So why not just use that data rather than trying to summarize the data in the form for some kind of a statistical description of it? Just use the raw data as is. Okay? And the only thing you need to do is sample randomly values from this list of values and repeat the calculation. So as you repeat the calculation each time, you're going to get a new distribution for an intermediate value and a new distribution for the next value, etc., until at the end you have an output value. Instead of being a single estimate, now you have a full description. A form of a simple histogram would be the easiest way to do it. So we have two questions. One is how many sampling of the data should you use? 1, 10, 100, 1 million. We need to have an idea how many times we're going to repeat these calculations. I mean, the computer doesn't care very much, but it will take a little more time to do it. And the next question is how we're going to use this output in the form of these histograms. So let's answer those two questions first. So let's say that you're sampling from data that's been described as a mean and a standard deviation that you have published. Okay, so this is your peer-reviewed data that your peers have considered that you did a good job, and they have approved your publication of that data. So if I take 10 samples generated randomly, or actually pseudo-randomly, because it's impossible to do fully random sampling, but this is pseudo-randomly sampling is pretty good. So let's say we take 10 samples, and assuming the red line is our real distribution. If we take 10 samples, I mean, those 10 samples are not going to describe very well the real data. However, if I do 100, now it gets a little bit closer. When I do 1,000, it gets fairly close. And after a certain large number, you can see there's actually not much gain. So somewhere there, I would say 1,000 would be enough. Now, this would be not very quantitative, would be just a very descriptive way of saying that 1,000 is good enough. But if you want to have a more rigorous determination of that number, what you can do is estimate the coefficient of variation of the output data that you are interested. So let's say you want to know what will be the microbial load of your final product of a certain pathogen. What you can do is then do the coefficient of variation of that output data, and you can see for different sampling size, this coefficient of variation at the beginning is fairly noisy, but is the sampling size, in this case 400, you can see it becomes more and more stable. Okay, so this is actually what we see here is actual data that we obtained in a publication on the our microbial load of pathogen in fresh oysters at different points of the processing, from the harvest to the process in the plant, and finally when the oyster reach the consumer table. Okay, so in this case, I would say 400, 500 would be enough. And we have done this type of coefficient of variation analysis so many times that now we know that if we do 1,000, it would be fairly good. We don't need to worry about that. So 1,000 would be a recipe if you don't want to do this analysis. Now, how do we use the output? So as I said, what you're going to get out of the analysis using this probabilistic method, we'll get some kind of a histogram of the output values. In this case, let's say this is shelf life, some arbitrary units, hours, days, whatever. And if you were to use the central value of that output, and you look now at the cumulative frequency curve, which is the red one here, you see that roughly you will have 50% of the values will be shorter than the shelf life for the mean values, will be shorter than these values here to the right, and longer than the one to the left. I mean, it's obvious, right? If you use a mean value, you have about a 50% probability of failure. And this is not acceptable. So what you need to decide is what failure you want. So let's say if you're looking for a product and you don't want to disappoint the consumers more than 10% of the time, then your shelf life will be this value here, not this value. So a much shorter shelf life. So now you can say that this value is what you can put on the label of that product, and you will be certain that in 90% of the time the consumer will be satisfied. You don't like 90%, well, just use 95%, and this will be the value here. So depending upon what failure probability you find acceptable, you can decide what shelf life. In the case of safety regulations that are coming now into play, the safety organization, they are using 95% certainty. They want you to demonstrate to them that you have 95% confidence that any batch that you're producing will be safe. So let's do a little bit of examples. So let's say that we want to sample normally distributed data. So let's say I want to calculate what is the average moisture of 2 batches of dried mango. This is data from this company. And this is the mean value and the standard deviation of 2 batches of this product. This is the mean, the standard deviation for 2 batches. And what we'd like to know is what will be the average of those 2 batches. So what I do first, I use the Excel function normal in INV. I enter a random number between 0 and 1. I enter the mean value that I have here. Okay, and I enter the standard deviation that I have here. Okay, so as I enter this information, Excel will generate one value that is normally distributed with these properties. And I do this 1,000 times. So I have here 1,000 values that were so calculated. And you can see now my sampling has the same value than my original data, which I expected. So here, almost the same again, okay? And the standard deviation, again, almost the same again. Now, it could be, if you are very unlucky, that you get a value that's different. And we have some publication which tells what the situation is like. If you have a coin, let us say true coin, and you send it, you flip it 100 times, you expect that if it's a true coin, you're going to get each side 50 times. If you get 10 times on one and 90 on the other side, then you will worry about the quality of the coin. Or it could be you're really unlucky. Okay, so lucky things do happen, and therefore we can deal with that. So if I use my formula that I gave you before, this is what I would predict to be the average for those 2 batches, and this will be the average standard deviation for those 2, and these are the formulas there. Okay. So, but instead of calculating this way, I can just calculate the average 1,000 times because I have 1,000 values. And I do that. This is the average now calculated from this data that I generated. And I can calculate now the mean and the standard deviation. And you can see they are very close to what I had predicted to be. Okay, so I can confirm here that this formula worked well. but also confirms that my 1,000 time calculations also will work. Okay, so let's say a different situation now. Let's say you are sampling data that cannot be described with a parameter like a mean and a standard deviation. For example, if you have oyster consumption data and you ask consumers how many oysters they have eating, you'll find that a lot of them have eaten 6 oysters, so there's a peak here. A lot of oysters, a lot of consumers eat 1 dozen. So here we have a peak at 12, and another group will eat even 2 dozen. So you can see here another peak at 24. And you have even one crazy consumer that ate 60 oysters in one sitting. Don't be surprised. When I was in college, I had a friend who had an oyster farm in the south of Chile, and every month he would go to the south of Chile, and he would bring to all his friends 1,000 oysters. We will sit in the afternoon, and I can assure you that we ate 60 oysters easily. Okay. I wouldn't do that today, but at the time I was young and silly, I guess. The other case could be that you have data of historical values you've previously measured, or whatever property, microbial load, vitamin content, moisture content, whatever data. You have lists of data and you would like to sample that. So in the case of the oyster consumption data, this is what we have. We have 306 consumers that we've asked how many oysters they've eaten. And so consumer 1 ate 1. I guess he ate it and didn't like it. Consumer 2 ate 2. Consumer 3 ate 3, etc. So consumer 56, a lot of 6. And then a few consumers ate a lot of oysters. Okay. So what I can do in order to generate a statistical sample of this data, I can say, okay, I want to have 1,000 values. And so I take a random integer between 1 and 306. So this happened to be 21. I go here to 21 and I'll find how many oysters he ate with this function in Excel called vertical lookup. And the answer would be 6. Etc., etc. So I'll do this many times, and I'll generate here 1,000 values of number of oysters consumed. The same procedure could be used to sample historical data. Very often also we find this situation where we have measurements that are below the detection and quantification level. So let's say, for example, you are measuring some pathogens in some almonds, for example, or the pesticides presence in these almonds. And it could be that you have something that looks like this. That 70% of the samples that were analyzed were found below detection level. So the test said 0. But you know that you are applying pesticides to those almonds. So saying that there is no pesticide at all, 0, is only thing you can say, that there was such a small amount that you could not detect it. Okay? Or it could be that the amount was so small, or the number of pathogens was so small that you could detect them. You know that you found one salmonella there or one pesticide there, but the amount was not quantifiable. Okay? And you find the rest of them were quantifiable, and you have some mean and standard deviation for that data. So again, now graphically, what we're saying that we have 17% are below detection. So this is my detection level. This is my quantification level. So 36% are above detection, but below the quantification level. And then the rest are in the quantification range. So I have here, in the case of microbial load, a certain mean and standard deviation for the log number of those counts. Okay. And in the case of pesticide, would be some concentration. Right? So what you do in this case is that you generate some number, 17% of whatever number you want to sample. Say when they were generated 1,000 values, so 17% will be 170 value would be detected between, will have concentration uniformly distributed like this, not uniformly distributed like this, between 0 and the detection level. 360 would be between this level and this level, and then 470 would be with generated with this log normal distribution. Okay, so again, 170 described like this, 360 described like this, and 470 described by this distribution. Okay, so now you have 1,000 values, and the next thing you need to do, and you need to randomize the 1,000 value. And then you can sample those 1,000 random value as in the previous slide. Okay, you need to do this randomization because otherwise you will have all the data grouped into below detection, above detection, and quantifiable, and it would not be fair for your sampling. Okay, so even one thing I find often is that people would ignore these samples and do their estimation for whatever process calculation or product design that they're doing based only on the quantifiable data. And that would not be fair for the sample description, because you are ignoring that so many of them, 53%, were below the detection level. And so using only this data would be incorrect. Now, this is also something that we have really enjoyed a lot to do. What do you do when somebody is asking you to estimate and you have no data? Okay, so you still need to come with an answer, and you need to provide an estimation for a process decision or a product decision, and you have no data. Well, there are two distributions that are really, really useful to handle this situation, as they're called. Two of them are the PERT and the triangular distribution. And these two distributions are defined by a minimum, a most likely value, and a maximum. And you say, how are you going to get those values if there's no data? Well, you ask experts. Okay, so if you don't have data, and for example, I'm living in Houston now. I've just moved here, and I don't know which is the likely summer temperature that I will face. And I'm sure that my friends here, new friends here in Houston, don't have data either, but I can surely ask them. And I'm sure they will give me fairly good idea what's the minimum temperature in the summer, what's the most likely temperature in the summer, and what's the maximum temperature in the summer. So experts have an idea based on experience of what is the level of these values. Once you have those things, if you use a triangular distribution, you just enter this as the minimum value. So the triangular with the minimum value is 0. A most likely value of 20, and a most likely value of 100 is a maximum. Sorry. With this data now, you can generate a distribution describing the data by this triangular function. Or if you want to use the PERT distribution, will be this curve here. Okay, and now you can sample and generate values. It will be between this minimum and maximum value, with this most likely value in between. Okay. So let's look at a few cases of application of probabilistic engineering. Let's say that I have in a bag, I'm putting some ingredients. They have different initial moisture content. So this one product is very, very low moisture content. One is higher. And therefore, during the life of the product in that container, the high moisture product will give some of its moisture. the low moisture ingredient will gain some of that moisture, and finally the product will reach some kind of an equilibrium. Okay, so there are many procedures available in the literature. Let's say that we have more than 2 ingredients, a lot of ingredients, and let's say we know the initial water activity for each ingredient, and that we know the slope of the isotherm in the region of interest. So the region of interest would be the small area here between the initial and the equilibrium value, and the initial equilibrium value, and these values are typically much closer. When we are talking about ingredient, will be fairly close. We're not talking about mixing a fresh piece of meat with some dry berries. I mean, that will not happen. Usually the product will have fairly similar initial but different water activity. So this slope here will be a fairly good description of the isotherm. And this is how much of each ingredient, described as the mass of solid of each ingredient. And then I have this approximation was published a long time ago and popularized by Dr. Labusa a long time ago too. So we have this formula to estimate what is the equilibrium water activity, and usually we have this as a restriction. We have an idea what should be the equilibrium water activity that we want to deliver to the consumer. So let's say that you have a mixture of ingredients. In this case, with raisins, 15 grams, dry pineapple, 15 grams, and you have also almonds with a water activity of 0.4. Okay, so you have determined that you want to have a final water activity of the mixture no lower than 0.65. Otherwise, your raisins and pineapple would be too hard to chew on them. Okay, so this is your question is what should be the initial water activity of those raisins and pineapple, so that after equilibration with your almonds, the equilibrium value is no lower than 0.65. So what should be this initial water activity for these 2 ingredients? So again, this is the data. So we want to have a final 0.65. These are the 3 ingredients. We fixed this to be at 0.4. Yes, for simplicity, we're saying the raisin, the pineapple will have the same water activity. And the field weight would be 70 grams of almond, 50 grams of raisin, and 50 grams of pineapple. So when we do this calculation using the formula I showed you before, you'll find that this initial water activity value that we're looking for should be 0.75. But this is the deterministic calculation, and we're ignoring variability. And we need to remember that at the very least, we're going to have variability in the initial water activity, and we're going to have variability in the amount of raisins that we're putting in the package. Okay, so this amount, my mouse is getting crazy. So we're going to have at least some variability in these amounts and in this water activity values. Okay, so we're going to assume that the standard deviation for this almonds, raisins, pineapple, in terms of water activity and field weight, these are the standard deviation. Okay, so these are the mean values, and these are the standard deviation. When we do a probabilistic analysis, and we look at this initial solution of 0.75 as initial water activity, we'll find that 52% will be below the target. It means that you will break the teeth of several of your consumers because you use a design based on deterministic calculation. If you do a probabilistic design and now you make your objective to be no more than 10% below the target 0.75, the answer would be you need to have obviously a higher initial water activity. So now with a 0.77, you will have certainty that your product will have few probability of being below the target and being below what the consumer will find acceptable. Obviously, you can also analyze for microbial stability, making sure that the product will be microbial stable. And there are many. I just analyzed here for the case of being so low that the consumer will find them unacceptable. Let's say now shelf life for moisture-sensitive products. Okay, a long time ago again, this formula were published by and made very popular by Dr. Labusa for the estimation of shelf life. And you can go back to the presentation and you can see here the description for this parameters in this equation. And in the 90s, we did a lot of work on trying to find equation describing isotherms, and this is the famous GAP isotherm model, and this just some parameters of that equation. So what we're looking here is that this is, we assume the product in this case is gaining moisture, so this is the initial water activity of the product. And as stored in a high humidity environment, it will slowly gain moisture. And finally, we'll get some value we consider unacceptable. So this would be the critical value. And if we leave it longer up to infinity, eventually will become to equilibrium with the storage relative humidity of that environment. Okay. But so we want to know how long will it take from this initial water activity to this critical level that we consider to be the maximum we want to allow this to happen. And obviously the reverse case is true. It could be that they're losing moisture if they are stored in a dry environment. So let's say that you are interested in estimating the best use data labeling. This is the data, the storage temperature, the relative humidity of the storage, the type of packaging you're using. This is the water vapor transmission rate. This is the relative humidity used for this measurement. And this is the package amount, the 100 gram. This is the area of the package. And the isotherm, we're going to use the GAP model for this case. And these are the properties of the product: the tomato slices, onion flake, sliced green beans are the three products we're going to look at. This the initial water activity, and these are some criteria to define the critical value. So in the case of tomato slices, we don't want to lose more than 10% moisture. And let's say that for the other two products, we don't want to exceed 0.4. Okay. If we do a deterministic analysis of this data using the formula I just showed you before, this will be the best use date that you will come for the three products: 243, 86, and 79 days. And we do a probabilistic analysis. As I will tell you, if you use mean values, you have half a chance of failure. So these are the estimated failure probability. Now, if you recalculate this, now using the probabilistic method I just presented to you, you fix the level of failure that you want to find acceptable. So let's say I fix it at 5%. Now the shelf life went from 243 to 211, from 86, from 81, and from 79 to 73. So if I use this data to label my product, now I have a 95% confidence that the product will not fail the consumer if they use it before this best use date. So let's say that I don't like the shelf life and I really want to have 180-day shelf life. Obviously, in that case, what I need to do is change the packaging material. So my question would be then, what packaging material can I use to ensure that I have a 180-day shelf life? So this is my criteria now. Okay, the rest of the information is the same. So if I do a deterministic analysis, this would be the field permanence that I will need to use. So I'll go to the supplier and say, I want packaging material with this property. Okay, they will understand what you want. If I do a probabilistic analysis of this value estimated deterministically, again, about 50% probability of failure. And I'm considering these two variability again, the packaging film variability and the initial water activity variability. The mean values are the same. If I want to do a probability design, still want to meet 100 days with now a confidence of 90%, so now failure risk is 10%, this would be the film permanence you need to request from your packaging supplier. So a 10% reduction in the moisture that is allowed to cross the film. Okay? Let me show you an example to see how simple it is to do these calculations. So I want to share with you in Excel. Come on. Come on. Okay, so I'm not going to go through how we built this Excel because it will take an enormous amount of time and it's not so friendly to do it in a webinar. But let's say that I'm doing my calculation here to obtain 180 days of shelf life. They want to have a 5 percentile failure risk. And in that case, this would be the water vapor transmission rate. This would be the permanence value for the situation. And this is the fill weight. Okay, so let's say that I'm done and my product has been on the market for a couple of months. And marketing say, you know, I have an idea. Why don't we come with a new and improved version of our product? And you know, consumers, they will not notice if we change the amount of fill. And when I give them 80 grams in the same package size with our new and improved version of the product. And really, the only thing you have changed is the flavor ingredient or put some colorant, which are not going to change the shelf life of the product to any extent. So you expect that the shelf life would be the same, being successful, being on the market with no problems. And now the only thing you're doing is changing from 100 grams to 80 grams. It happens. Believe me, it happens. So now you can see by changing the package content from 100 grams to 80 grams, my shelf life is 144. And it's obviously they should have predicted this to happen because if you have less product in the package of the same size with the same packaging film, the amount of water that's entering the product has less product inside, and therefore the impact on the moisture content of the product is higher because a small amount of product in the package. So I need to, if I want to do this business, what I would need to is to recalculate what should be the packaging material. And that's what I really wanted to show you. So you go here to Excel on data and what if analysis, go seek, and you say, I want to have this cell, which is my shelf life, I want it to be 180, okay? And I want to accomplish that by changing the packaging water vapor transmission rate. So I change it, and now I'm done. And now I say okay, and you can see I have here 180 days, 5 percentile, but now my water vapor transmission rate value has changed. Okay? So you can see that once you have built the Excel spreadsheet, recalculating anything in terms of this probabilistic analysis is fairly simple. let's say that I want to change this from 5% to 10%. So now 0.1. So now I want this to be 180 days. So I go again, data, what if analysis, go seek. I want this, I don't need 190, I just need 180. Again, I go change the packaging material. And done. Okay, so as you can see, it's fairly simple to recalculate your process decision, whether it's the amount of product, the shelf life, the percentile risk, whatever you want to calculate. It's a fairly simple system. Works to build the Excel spreadsheet. But typically, when I do this in workshops that are offered to industry and courses in academia, in about 2 or 3 hours, we can build any of these spreadsheets. And I think with that, all I have to do. Come on. So I'll give you the example, and all remaining to me is to say thank you. And if you have any questions, please let me know. This is me and my wife enjoying life in Oregon, where we were living 2 weeks ago. And now we're in Texas, and I guess we're not going to be doing much mountain biking, but for certain we'll find enjoyable things to do in Houston too. Just all take some flexibility and imagination, and you can enjoy life anywhere in the world. Thank you for your attendance, and thank you for your questions if you have any. Thank you.
Thank you, Dr. Torres, for sharing your knowledge with us. Let us start the question and answer portion of the webinar. Remember to unmute your microphone if you want to ask a question. Otherwise, you can write it on the chat and I will read it out loud for you. Do we have any questions from the audience? Well, I'll start with one, Dr. Torres. So the application of probabilistic engineering, how do you think it's, do you think this is something that we should be teaching in schools right now? Do you think a lot of engineers are learning this at schools at the moment?
I mean, in most other engineering fields, and I mentioned specifically case of aeronautic engineering, this is for sure. Or even in other fields, for example, business schools. Imagine when they are investing $10 billion, they want to make sure they have a good idea of the risks that they're running when they invested that much money. And therefore, they do a lot of this probabilistic type of analysis to have an idea of how risky it is. As I would say, and the risk is also very dependent on the person who is making the decision. For example, if you ask me how much risk am I willing to have if I have $100 that I'm going to invest in something, I would say I don't really care much because $100 will not affect my living. But when I was a student, I can assure you that $100 would cost me a lot of trouble if I lost them. So the risk is something that is very much dependent upon the situation you're analyzing. So, for example, in the case of food safety, which is one of our important concern, as I said, we still make 1 out of 6 people sick when we give them food. We are having a lot of more interest from the government to reduce that risk as much as possible, because health in time away from work time away from life, meaning you're dying, is really expensive for society and for the company and for the government. So regulations that are coming now into play, they are requesting you to ensure that all your decisions are supported by statistical analysis that shows that you have a 95% certainty that the product design and process design will not fail. Now, from a teaching point of view, what I found in my experience, that probably the most valuable consequence is that students learn to appreciate that if you have a poor measurement data, so they're careless in the lab when they're measuring whatever property you have assigned them to. In the past, they would give me 3 values, so they replicate, and they couldn't care that the standard deviation of those 3 values or the variability of those 3 values was huge. But when they start applying that variability in design and a process, they find that if the variability is huge, for example, for microbial load, it would mean that in order to be certain that your product is safe, you will need much more processing time. And processing time is the most effective factor in any product. If you ask industry, all they are asking continuously is how can I make my process time shorter and shorter and shorter and shorter? We are constantly being asked to please reduce processing time.
Thank you, Dr. Torres. We have a question from the chat. Ramon Verduzco asks,
Can I ask a question, Mom?
Oh.
Sorry, Mom.
Go ahead, the oral question. I'd like to hear the oral question.
Okay, Doctor, thank you very much for your informative speech. Actually, my question is, you selected a gamma function as a probabilistic curve for stochastic calculation. Why not such beta curve with negative skewness and either normal distribution? Is it possible for deterministic stochastic calculation?
As I said, I mean, my first preference is to use the raw data itself. So if you are working at a company, my suggestion is to use your historical data. A few years ago, we worked for a large company that wanted to gain market share, and they were having trouble meeting the shelf life they were claiming on their product. And since they had 3 years of data for the product and process and distribution conditions, we asked for that data to make the prediction. So the best thing is to use no statistical distributions at all, just use the raw data, okay? Because that describes perfectly the real situation without any approximation by any statistical distribution one apply. On the other hand, yes, you can use any, and we have used this example of an application we've done, but there is no limit in the statistical distribution you use. Now, one of the most commonly used that give us the most trouble is actually the normal distribution. And the reason for that is the normal distribution goes from minus infinity to plus infinity with certain mean value. And sometimes you get extreme values that are very low probability, but every now and then they occur and they mess up our calculation. So if you use historical data, that will never happen because you will never have data that is impossible. So sometimes we get negative process time or negative moisture content or negative concentration because the normal distribution can go from, it can include a negative data. So any distribution that avoids negative values, which are typically nonsense in our physical world, is best.
Thank you, doctor. Thank you.
Okay, the question from Ramon Verduzco was, is it possible to use Bayesian approach in these cases or in others?
You understand what you mean by variation approach, but what I want to emphasize is that this approach can be used for any situation at all. For example, 2 years ago, one of my former students called me and said, can we use this to control the fill weight of a packaging line? And his concern was that they had a new contract with a very large distribution company in the US called Costco. It's an international distributor with presence not only in the US, but also Canada and Latin America. So having a contract with Costco or with Walmart or one of those huge distribution company is fantastic, particularly when you are a medium-sized company, because it means you're going from small volume to huge volume. Okay, so his concern was that, well, if we don't control the filling weight of our packaging slide, maybe we are giving away product and therefore we're giving away profit. Or the other hand could be if we have an underweight product reaching this large distributor of this company's product, they were concerned that the company would close a contract because they were not meeting the specified weight. And Costco, for example, is a company that's very high reputation among consumers that they deliver what they promise. Therefore, they were concerned that they could also have underweight. So we did, instead of talking about specifying a certain percentage of variability of the weight for this filling line, we attacked the problem as risk analysis. We said, what would be the consequence of having an underweight? There would be a penalty for an underweight. And so we gave X number of dollars for that risk. And we looked for what should be the filling weight that should be specified on the packaging line, so that given the variability of any packaging filling device, that you would manage to reduce the risk. And I said the risk could be the risk of the penalty and the risk of giving away product. And we found out that the penalty level had almost no influence in the decision. So we could recommend a filling weight specification given the variability of the packaging line that they were using that would minimize the risk. We have done microbial shelf life. We have the meat products. When will they fail? We have done design of processes to inactivate an enzyme. What should be the process condition that will give us a certain percentage of inactivation of enzyme with a given confidence level? So it really doesn't matter what application you have in mind, as long as you have been able to do it in the past using the deterministic approach. The only thing you're doing now is repeating the same calculations you have always done. Thermal process design, it doesn't matter what you're talking about. You can do them using this probabilistic approach. Just repeating the calculation a sufficiently large number of times. And I said that if you want a recipe 1,000 times, repeating the calculation is more than enough. And when you do the calculation in Excel in just a normal laptop, it doesn't take more than a few seconds to do the calculation. You saw in the case that I illustrated in this webinar that the computer took no time and optimized the response to whatever question I asked on the Excel, and it was doing all those calculations with many, many formulas and with 1,000 values each. One comment is that often I've taught this in workshops. Typically, I recommend a 2-day workshop or at least a 1-day workshop. So if anybody is interested in such a workshop or a short course in your university, just let me know. Sometime I travel close to your location. I don't know where you're located, but since I travel a fair amount, adding another stop or 2 or 3 in my trips, I would really enjoy doing the presentation in the workshop. So just let me know.
Can I ask another question?
Yes, you can.
Yeah, sorry, I should introduce myself. I am Mehdi from Iran. Doctor, thank you for first question. Answer to the first question. Actually, if we don't have any idea about the data, we don't have any historical information about our data, which type of distribution is more appropriate, negative skewed or positive skewed distribution?
As I said, in that case, the 2 distribution that we use the most in our case has been the triangular, which is very, very simple. It's even built into Excel. So to do anything. Per distribution is another one which is really useful. It can be used with a free downloadable application from the web. Today, all kind of tools to do the generation of data following most statistical distribution you can think of are easy to find in the literature.
Thank you.
Ramon, also thank you for your answer. Sorry. Does anyone have more questions?
I have a question.
So Diana's now raising a hand. I don't know what it meant.
Yeah, thank you. It's just well, I'm wondering, is there any way of controlling whenever you are unlucky with the generating of the data? You know, when this data and the experimental data do not fit or something? Is there any way of knowing that you are unlucky and it's just not working?
Sorry, Diana. Could you repeat your question again?
Yes. Can you hear me now, Doctor? Hello.
I think he muted his microphone so he could hear you better.
Oh, okay. So just, well, my question is, whenever you are, well, in the case of your calculating all these things and you are unlucky, is there any way to, well, unlucky in the way that Dr. Torres mentioned, that the data generated is quite different from the experimental data? Is there any way of knowing or controlling this situation?
Yes. The answer is yes.
Okay.
Okay, so can you mute your microphone now? Okay. As I said, it's always possible to be unlucky, right? And as I mentioned, the case of tossing a coin, right? Even if you use a good coin, you could be unlucky. Okay, so we have a publication where we were very concerned about generating data that could have too much deviation from the original true data. So I'm assuming that your published data has been peer reviewed and your data is good. And if you're working in a company, I'm assuming that the data that you've been accumulated has gone for all kind of procedures to ensure that the data is good. So if the starting data is bad, well, nothing will help you, right? But so I'm assuming that the data that you have, either from historical records or from peer-reviewed publication, is good. So I'm now trying to replicate the variability of data using some of the procedures I mentioned in this webinar, and I want to make sure that the sampling that I've done is good. So we are very concerned about that when we're designing a thermal inactivation process to eliminate Clostridium botulinum. And that's obviously something you want to make sure that your calculation is fair, as correct as possible. So if you contact me, I can share you that publication where we came up with some procedures to estimate how much was the acceptable deviation of the generated data from the original data. Okay. That's one case. The other case is we've done, for example, the case of shelf life prediction. We have predicted how much moisture content you should gain during the storage of a product, and we have followed the storage of sample of the same product, and then compared our prediction and the availability of our prediction with the real storage data in order to have confidence in our comparisons between predicted data and experimental data. The number of samples that we included in the study, I think it was about 200 samples. I mean, very rarely you will find any storage experiment with 200 samples, either 100 or 200 samples. And therefore, we have confidence that that our comparison was a good one. So you can do an experiment with large number of samples to validate your predictions. And once you have validated your prediction, you are confident that your calculation procedure is working, therefore you can apply to other conditions. Or you can follow a statistical procedure to assess the deviation of the generated data from the actual measurement data that you have collected. Both we have done. And we can share the publication if you contact me.
No, okay, thank you. Yep.
Thank you. Good question.
Do we have any more questions from the audience? Well, if not, let me thank you again, Dr. Torres, for this interesting talk. And thank you all for participating. Next month, the webinar will be presented by Dr. Christina DeWitt, an associate professor and director of the Seafood Research and Education Center of Oregon State University. This webinar will be on May 22nd. And just keep tuned on our website and our Facebook page for more information regarding her presentation. Thank you again, Dr. Torres, and thank you, everyone.
Thank you for the audience, and thank you for the questions. They were excellent. They made me think. That's good. Thank you. Have a good day.